Hi, welcome to this video on solubility and the common ion effect. So in this video, we're going to be talking a little more about solubility equilibrium, but we're going to be focusing on solubility equilibrium when our initial concentrations of ions are not zero. So we're going to be starting with some amount of our ions already present in solution, or we're going to be talking about if we were to take a solution that was already equilibrium and then add one of our common ions, and it could cause a precipitation reaction. There's lots of things that could happen. But how that actually affects the equilibrium and how we would do equilibrium calculations. So, first off, experiments show that when we have the solubility of any salt and we calculate it when it's without ions, right? When we just take the salt and put it in water, we can calculate our KSP. When we add in, and this is important, when we add in a common ion, which means one of the ions that was dissociated, what we're always going to see is that the solubility is always going to be slightly less. So that means if I start with some of that ion already present, then I'm going to reach equilibrium faster, and I'm going to see that, or not faster, not in kinetics world, but I'm going to reach equilibrium sooner, and when I do that, it's going to be at a lower concentration of that ion. So we're going to see less solubility occur. This has to do with LeChatelier's principle. So when we start with an initial value of one of our ions, then we already have some quantity of product. And so that amount of product is actually going to shift back to the left, right? Or to the reactants, which essentially means it's going to remove ion, or less ion is going to be proceeding in that product direction. pH can also have an effect on our solubility, so that's important, okay? So we haven't really talked acids and bases yet, but we will, and we'll talk about this a little bit more as well. But pH, whether my solution is acidic or basic, can actually have an effect as well, because if I have a solution in which, for example, magnesium hydroxide, right, this is a basic solution because it's got the hydroxide, it's a milk of magnesia. It's what's in Pepto-Bismol. And so when I take this, we know it's soluble slightly, right? And I've got these hydroxide ions floating around. Well, when I add an acid or a base, that's going to affect my solubility a little bit as well. So, for example, if I were to add a base, like hydroxide, correct, something else, that's going to increase my amount of hydroxide. And so when it does that, right, if I add a base, right, then what's that going to do? That's going to actually decrease the solubility, right? It's going to shift it from our LeChatelier, because it would shifts left. Let's pretend that says shifts left. Okay, so if I increase that hydroxide, that's going to shift it left. But if I add an acid, which in this case would be H+, right? When I look at what's going on there, what we would see happen, again, according to LeChatelier's principle, is we actually would see the acid, the H+, would react with the hydroxide. And so then that's going to end up with H+ is going to end up making waters. So that's going to decrease my hydroxide. When that happens, that's going to shift right, which then is going to show an increased solubility. We'll have more ions dissolved. Increased solubility. So we would get more ions to be dissolved. So pH can affect it. So if I put something in that is a low pH into this scenario, we would actually see an increased solubility. But if I put enough more base in there, that's going to decrease it. So pretty easy to see and kind of figure that out. So we can also do calculations to find what is the actual concentration or solubility when that common ion is present. It's the same as the previous calculations. The only difference is we're starting here with something already in the solution. Whereas before we were just saying, oh, well, with our initial amounts, or our initial amount of solid, and we were assuming there was no ions already present. So in this scenario, right? First off, we're going to see the solubility of calcium fluoride. So that means we're going to have calcium fluoride, right, plus water, that's solid. And we're going to see when it reaches equilibrium, we're going to have calcium ions, right, Ca plus 2 ions, and 2 fluorine ions. Now, when I do my Rice table, right, my initial quantities, I don't really care about my solid again, right? Normally, we would say my initial quantities are 0 for calcium and fluorine, but that's not the case because, do you see that? We have this. Well, this is very soluble. Everybody okay? So I know that this is very soluble. It's one of our always soluble rules, right? Because it's an alkali metal and it's a halogen, right? So it's very soluble, so we would consider that to be almost 100% soluble based on our general solubility rules. That means its KSP is going to be very close to 1. So when I break this apart, I'm going to have 0.025 molar sodium ions, and I'm going to have 0.025 molar fluorine ions. So basically what it's saying is I'm going to add the calcium fluoride to a solution that already has a common ion. So my initial amount over here, I still don't have any calcium, but I'm initially starting with 0.025 molar of those fluorine ions because I already had that in the solution before I added the calcium fluoride. Now, hopefully you realize if I start with some of that, that is not going to be ideal. It's not going to like it, right? You could calculate a Q from this if you wanted and see what it's going to do, but hopefully you realize that means that there's more fluorine. So that means I'm going to basically shift to the right less. Doesn't mean I'm not going to make any product. I'm just not going to see as much being made. So according to my Rice table, I would still see a plus X, right? And plus 2X going on here, right? And so at equilibrium, though, I'm going to have X calcium, and I'm going to have 0.025. Let me erase that and rewrite that. I'm going to have 0.025 plus 2X. Okay, so that would be what I would see at equilibrium. So now what we want to consider is, and I'm going to move this up a little so I've got a little space to write. You may need to have to squeeze this in, sorry. So now that I'm looking at this and I see what I have quantity-wise, right? I could easily solve for X. So I'm going to write a KSP expression, right? So my KSP will be calcium plus 2 times fluorine minus 1 squared, right? Because there's 2 of them in the equation. And then we would plug in what we have, right? So we're going to have our KSP, which is going to be 4.0 times 10 to the negative 11 is going to equal X times 0.025 plus 2X. Now, this could get really complicated. And what we could do is we could, once we distribute the X in, we could solve with the quadratic formula, right? So we could distribute in and we end up with X and X squared, and then we do A and B and C, and then we, right, set it all equal. But we're not going to focus on using the quadratic formula because the AP exam is not going to require you to do that. Now, I may do a problem or two like that in class with you just to show you overall. But here's essentially what I'm going to point out to you. And hopefully this will make sense. When I look at this KSP value, negative 11 is really tiny. So that means there is hardly, like, we're talking point, whatever, 10 zeros and a 1 change in concentration for those ions, right? So when I say that I'm going to take I'm going to start with 0.25, keep in mind this is 2.5 times 10 to the negative 2 10 to the negative 2 and 10 to the negative 11 is a huge difference in concentrations. So even when I increase by 2x, that increase is going to be super small. Like so small, right? That it's not going to change 2.5 times 10 to the negative 2. It's not going to change that thousandths place, right? So therefore, I'm going to do what we call in AP, neglect the x. So I only do it with the plus or minus part, and I can only do it when it's a really small KSP value or a K value. If it's less than basically negative 5 and smaller, we can assume that whatever, even if I did the quadratic, which believe me, I'll do one for you in class, even if I did the quadratic, the x quantity is not even going to change the 0.025. So I could go through the whole process of solving for quadratic with the quadratic and finding the x and then plug it back in, and I'm still going to get 0.025. So that's why we neglect that plus x. Now we do not neglect the x of the calcium ion because that's not adding anything. So that is its own quantity. Okay, so then from here, that makes our math a little easier when we neglect that because we know it's not going to change much. And we're really just going to divide by 0.025 and make sure that's squared. Okay, so I forgot to put my 2 up there when I was doing that. So then we're going to divide by on both sides, right? 0.025 squared. Okay, so when we do that, our x, which is the concentration of calcium ions, which is also equal to, right, the solubility of CaF2, right, how much it dissolved. We solve it, we whatever, divide, and we end up with 6.4 times 10 to the negative 8th molar. So my solubility is going to end up being smaller than what it should have been. Okay, that's important. So if I reworked the problem and we did not have the sodium fluoride present initially, what we would see is we would see a higher solubility value. So it would be something that would be bigger than 10 to the negative 8. So because I have that common ion present initially, that's going to decrease the solubility of that salt. All right, so another thing we could have done, and we didn't do it on that problem, it wasn't that big a deal because we were just trying to find the solubility, is we can still solve for the reaction quotient. The reaction quotient, or Q, is important because when we're looking at Q, that can help us decide, right, if we're going to form a precipitate, okay? That means if we exceed the, if we cause something to happen in the reaction that then is going to shift the reaction to the right. Not to the right, to the left. So when we're talking precipitates, those are going to be shifts to the left, right? Because if we shift to the left, we're going to make more solid, which means we're going to precipitate. And then what kind also lets us know what concentrations of ions are required for a precipitation to happen. So there's different ways we can calculate different things with this. So when we calculate a Q, that's using those values that are not at equilibrium, and then we compare it to what we know the K value is. So when Q is less than KSP, right, that should make sense because that's going to mean that I have more reactant and less product. This is when we're unsaturated. So that means that I may have added a little bit of salt, but I didn't add enough to completely saturate the solution, okay? So I could add more salt and it would still dissolve that additional salt. When Q is equal to KSP, that's when we're saturated. So that is when we reached equilibrium or we're like maxed out, right? If Q is greater than KSP, that's going to mean there are more product ions. Remember from first year, hopefully, that you remember that this is more ions dissolved than what would theoretically be possible when we're supersaturated. So that's not ideal. It doesn't like that. So if I have too many ions in my solution dissolved at that beyond that KSP value, it's really, really unstable. And so remember, that has to do with the arrangement of the water molecules, and it basically is tricking the water molecules into thinking that they can dissolve. But any disturbance, any addition of more solute or something along those lines will actually cause a shift backwards. And then that's going to end up causing a precipitation. So precipitates form when the solution is supersaturated, because it's going to shift back to the left. And that's the key. So it's very unstable. And so it will always shift back to the left whenever it's supersaturated, because it doesn't like that. It's not going to stay that way for long. It's unstable. All right, so let's talk a little more about precipitation. So we can also do side reactions that cause precipitation of insoluble salts, right? So for example, there's some metal-bearing ores that often contain the metal in the form of an insoluble salt. And so then the ores often contain other metal salts and things like that. We can dissolve metal salts to obtain the metal ion, and then use precipitation selectively to get stuff. So we can do side reactions to make things happen and get stuff we want. I'll talk a little more about these later, but it is possible to use this to our advantage and get things we want out of it, okay? But a lot of times those require calculations like KSP and Q calculations to figure out how much of whatever it is I need to add to get out what I need and things like that. So the math can get a little complicated here, but not too bad. All right, so let's start here with, I'm actually going to move that down just a bit. So let's start here with this example. So in this example, there is a reaction, right? And it says a solution is prepared by adding 750 milliliters of 4.00 times 10 to the negative 3 molar cerium nitrate, right? So here's what we're adding. Nice, okay. To 300 milliliters of 2 times 10 to the negative 2 molar KiO3. All right, so first thing I like to do is just write my reaction, because I like to see the reaction written out and see what's going on. All right, so the other thing is we're asked is, will it precipitate? So that means if I want to find that, I'm going to be looking for Q, right? Because I need to know where is Q compared to KSP, right? To know if it's going to precipitate. So that means we need to know what those initial quantities of each of the substances are. So it gave me that. So I'm going to show you the reaction first. So we have cerium nitrate, so CeNO3, 2. And we're going to react that with KiO3, right? And when we do that and we react, a lot of times they'll ask you now on the AP exam to actually write the reactions just because they want to see that you know how to do it. And so we know we're going to make cerium iodate, IO3, and KNO3. And if we look at our quantity-wise, right, if we balanced it, we would have 2 KIO3s for every 2 KNO3s. So easy to see what we're looking at. Then we look at our numbers. This is why I like my reaction to be written out, is because I like to see what I have. I have 750 milliliters of 4.00 times 10 to the negative 3 molar. So hopefully you can quickly, easily see this, right? When I take these and I multiply volume times molarity, I'm going to get my answer, or I'm going to get moles, millimoles to be specific, because it's in milliliters, which is fine. We did this earlier in the year. Millimoles are fine. Like, you don't have to get rid of the milli. It just makes the number nicer. So in your calculator, if you take 750 times 4.0 times 10 to the negative 3, that's going to give you 3, and it's 3.00 millimoles of this substance, right? And then I'm going to do the KiO3, same scenario. I've got 300 milliliters. Remember, we always want to show our work for this. So that's why I'm showing it down here, because I always want to make sure I'm including what my work is for the AP exam, just in case. You never know what they're going to count as points. times, okay. So when I multiply 300 times basically 0.02, I end up getting 6 millimoles. So 6.00 millimoles. All right, so that's important to kind of see because that's how much of each I have to start with in moles, right? So if I have to think about product or solubility, that's also very, very important, okay? The other thing is, so that's how many moles of each that I'm going to add, all right? So now here is where we need to get into our problem. So we need to look at what it's asking. So it wants to know if CeIO3 will precipitate from the solution, right? So what we're going to do is we're going to actually take, so I just wanted to see the reaction. This is what I have initially. So I want to keep in mind, these are my initial moles. Yes, everybody okay? So that's initial moles of each substance. So I'm going to go ahead and start with writing my KSP expression. So I've got CeIO3. Now the reason I'm going to add the KSP, and I'm going to leave the water out just for space purposes, I don't really need it. It's going to be cerium plus 3 and 3 iodates. So the reason that I want to write my, or do my equilibrium expression is because it's asking about precipitation, which means I'm going to need a Q. Okay, so here's the reaction that we know we need in order for precipitation to happen. So what we're trying to figure out is this going to shift left or shift right is basically what I want. So to precipitate, I need it to shift left, okay? And then if it shifts left, then my answer would be yes. It forms a precipitate, okay? So that's what I want. That's the key, all right? So I need to consider what my initial concentrations of those ions are. So remember when we set up our rice table, I really don't care about the amount of solid that I have. But when this reaction happens, right, I end up with this, right, as a product, and then that as a product is then going to come together, and so then I'll only have some ions left in solution. But initially, here's the ions I have of each, right, my millimoles. So what I need to do is I need the initial concentrations of each of these. So remember that this is a net ionic equation. Really, the cerium plus the iodate is making cerium iodate. Potassium nitrate is a spectator, it's not included. So this is what I have, or what's happening. What I need is initial concentrations of cerium and iodate. So with concentration of cerium plus 3, right, initial, I'm going to put a little I here, or 0, is going to be my moles, which is 3.00 millimoles, right, divided by my total volume of solution. Now this is what throws students off, is my total volume of solution initially is actually going to be both of those added together, because that's the total volume when I combine them. So it's really going to be 1,050 milliliters. So that's going to give me a concentration of cerium plus 3 initial before the reaction. So keep in mind, initial, this is before the reaction. Okay, is what that initial is. That's what we're looking at. Is going to be 3 divided by 1,050. So that'll cancel out your milli. And when I do that, I get 2.86 times 10 to the, let's go, -3 molar. I do the same thing to calculate my concentration of iodate ions, right, that I initially had. And so in that case, I had 6 millimoles, but still out of that 1,050 milliliter solution. So again, when I calculate these out to find what that initial is before the solution, before we actually reacted and made anything happen, I end up with 5.71 times 10. It's a decimal. It's really ugly. Hold on. Let me re-erase. I know I'm struggling with my handwriting today. 5.71 times 10, and in that case, -3 molar. Okay, so those are my initial quantities that I started with molarity-wise when I mix them, but at the beginning time 0 when the reaction begins, okay? The reaction happens, right? So we know the reaction is going to happen. What we're trying to predict is, does the reaction make more product or more ions, or does the reaction shift left and make less because we already have too many beyond the solubility point? So that's the key here. So we don't really care as much about the equilibrium at this point. What we care about is Q. So QSP, right, is going to be cerium plus 3 times iodate, IO3, minus to the third. Okay, so when we plug in for this, I'm going to lift this up just a bit. So when we plug in for that, right, we're going to take those quantities that we have and we're going to solve for our QSP. So our QSP initially, starting off, is going to be 2.86 times 10 to the -3. And then we're going to multiply that by, molarity, almost left that off. And then I'm going to take that by 5.71 times 10 to the -3rd molar, and that's going to be to the third. So when we calculate this out, our QSP is going to end up being, when you take that and then cube that 5.71 times 10 to the -3, and you multiply them together, is going to be 5.32 times 10 to the -10. So then what we want to do is we want to do a comparison, right, to determine when I start with these initial common ions. So this is also a common ion problem because I'm starting with these common ions and I'm trying to decide, when I already start with this amount, what happens? Does it shift it, or does it shift it right, or does it shift it left, right? Do I make more? Do I make less? So QSP in this scenario, right, is going to be greater than KSP. Well, because the KSP, if we go back into the original problem, right, was 1.9 is up here. 1.9 times 10 to the -10. So I'm going to write that in just so you have it. So that's 1.9 times 10 to the -10. Okay, so obviously 5.32 is bigger than 1.9. So we know QSP is greater. So what does that mean? That means that your products are larger than they should be, right? Are greater than they should be at equilibrium. At equilibrium. So that means basically I'm beyond the saturated quantity. So I'm oversaturated or supersaturated. So my solution will not like this. And so in this case, if I'm supersaturated, my reaction is going to, the reaction shifts left, right, to actually convert some of those ions back into solid, which means it will precipitate, or it makes precipitates and settling more solid on the bottom. I hope that makes sense. So if KSP is greater, we know that there's more products than there should be at equilibrium, so we're supersaturated. Unstable, that means we're going to have to basically shift back, use some of those ions, and decrease that solubility content. Okay? All right, let's go on to one more. Okay, so in this problem, it's going to be very similar to the other one, but it's going a little step further. So the one we just did is very similar to this, except this one's going to ask us to actually calculate the concentrations of magnesium and fluorine when they're at equilibrium with solid MgF2. So we actually have to do the reaction and plug those values in, right? So we have to figure out the limiting reactant after we decide if it's going to precipitate or not, right? If it's going to shift left or shift right. So that's really all we're looking at. So in this problem, we're going to start, again, I like to start with the reaction. We really don't need it till later, but I just like to start with it. So I've got MgNO3 2, okay, plus I've got NaF, right? And I'm reacting those two things. When I react them in this double replacement reaction, I end up with MgF2, and I end up with sodium nitrate. And so again, knowing what's going on, we got 2 here and 2 sodium fluorides. We know right away when we look at what's happening, I would just like to point out, this is the solid that we're making, okay? We're not making, or at least what the equilibrium we're concerned about. Sodium nitrate is very soluble, so that means sodiums and nitrates are not going to be participating in the reaction, really. We're looking more at magnesium and fluorine ions, right, and how they react. But we're going to start with that initial quantity. So I've got 250 milliliters of magnesium nitrate, and I'm not going to write it as 1.00 times 10 to the negative 1. I'm just going to write that as 0.1 because that's easier to write, because that's the same thing, right, in scientific notation. Oh, it would help if I wrote the right things, wouldn't it? I'm sorry, I'm wasting your time. Okay. All right, so I'm going to write the correct things. I have 150 milliliters of, and that's 1 times 10 to the negative 2, so that's really going to be 0.0100 molar. And I have 250 milliliters of sodium fluoride, right? And that's going to be the 0.1 that I was talking about, okay? So then from there, I can multiply these and find how many moles of each I have initially, right? So 150 times 0.01 is going to give us a nice quantity of millimoles. That is going to be 1.50 millimoles, okay? And that's millimoles essentially of magnesium plus 2, right? And then I'm going to have 25 millimoles, that's a huge number, millimoles of, what is that? Oh, the fluorine. Okay. So now from here, one of the things that's important to think about, and I'll bring back up later, is which one's going to be the excess and which one's going to be the limiting reactant, right? So here is kind of nice, easy math when you do millimoles. It makes the numbers nicer. For every one of these, I use 2 of those, right? So if I have 1.5 millimoles, I'm going to use 1.5 millimoles, and I'm going to have 0 left, right? So that means that for sodium fluoride, I'm going to use 3 millimoles. Hopefully that makes sense. And when I do that, I'm going to have 22 millimoles left. Everybody okay? So this is definitely the excess reactant in this scenario, and this is definitely the limiting reactant. I just want to point that out. So it makes it easy when you have it set up in millimoles like that to do the stoich when the stoich's nice, right? Because I already have it in moles and I can just easily see the stoich. Now you can do the stoich for limiting and excess and find the amount of each and then identify it that way. This is just a little easier because then we can see how much excess is left over. Okay. So remaining. So that's how many moles are remaining. So this is going to be important later because what happens is that becomes a common ion, right? So in the solution, we're going to end up having 22 millimoles that are not going to react. They're still going to be present in the solution. And so that's going to cause an effect or a common ion effect later, okay? So we want to consider that later. I'm not going to talk about that yet. So the other big thing we want to talk about is the reaction going to shift left or shift right? So we want to decide, are we going to create a precipitate or are we going to create more ions, right? So what I'm going to do is I'm going to go ahead and set up, find my initial concentrations, right, just like we did before, to determine if it's going to precipitate or not. So we're going to find our concentration of the magnesium ions initially, right? So it's the same thing we just did. We know we had 1.50 millimoles initially, and our total volume of the solution, 150 plus 250, is going to be 400 milliliters, right? So then that means that this concentration is going to end up being, sorry, I have to figure that one out, 3.75 times 10 to the negative 3 molar, okay? And then same thing for my fluorine ions. My concentration of fluorine ions initially, when I put those in there, are going to be 25 millimoles. Now remember, we've already decided this is going to not be all used up eventually, but it's what we start with. And so out of 400 milliliters, right? And so in this case, that's going to end up being 6.25 times 10 to the negative 2 molar. Okay. So then I'm going to plug that into the KSP expression, right? So my KSP expression is going to be the concentration of Mg plus 2 times the fluorine concentration squared. So when I plug those in, I'm going to take 3.75 times 10 to the negative 3rd molar. And I'm also going to take 6.25 times 10 to the negative 2, and I'm going to square that because there's the square in there's two of those in my equation, right? And so when we go to find this, okay, for MgF2, oh, I forgot to write that for you, the equation. So Mg, I'll write it in a minute, but where I was getting the KSP expression. Hopefully by now you know where I got it, because obviously we've done a whole bunch of these. So my KSP is going to be, when I calculate that out, 1.5 times 10 to the negative 5. Okay. Times 10 to the negative 5. So now, looking at this, I'm going to have to go down to the next little bit of problem because I'm out of room. But when I look at, this is QSP, pretend that was Q, that I wrote a Q. All right, so my QSP, right, is 1.5 times 10 to the negative 5. My KSP is 6.4 times 10 to the negative 9. So obviously this is larger. So QSP is greater than KSP. So since my Q is larger, it's the same scenario as before. The solution or precipitate will form, right? We're supersaturated, so a precipitate forms. So what's going to end up happening is we're not going to have extra of those ions. We're actually going to use up the ions, right? And the reaction is going to happen. So we will shift back to the left, okay? So that's the key here. So it's going to actually, the reaction's going to happen. It's going to shift back left. Once I know that that's going to happen, right, I know that I'm going to use, that's how I know I'm going to use 1.5 and 3 millimoles, because those have to get consumed so that I can use up all the magnesium ions that I had present when it shifts. Hopefully that makes sense, okay? So the problem becomes is I still have fluorine ions, but they don't have any more magnesium ions to collide with. So to actually answer the question it was asking, I have to do a little rice table, okay? And so that's why it was important that I thought about the limiting reactant up there and what was going to run out. So really, so when I go back to it, I've got MgF2, right? And that's going to dissociate into magnesium plus 2 and 2 fluorine ions, okay? After the shift happens, right, I now have all of this excess, right, remaining. So we now have a common ion problem, because it's not just that I have a common ion that's going to cause a shift to cause a precipitate. I now have a common ion that's going to affect the ability of any of the magnesium fluoride to dissolve anymore. So that's going to slow that down, right? So I have to consider the fact that this gets consumed, And then that's going to affect my concentrations of magnesium and fluorine. And it's going to affect my overall concentrations at the end. So I'm going to do a quick rice table. Okay. So now, again, we don't care about our solids. But magnesium, we know we have 0 of because it got all consumed, right, in the reaction. But fluorine, now here's where I have to remember, I've got 22 millimoles, right? I have to divide that by the volume of solution. So we have to remember that I have 400 milliliters of solution, and I have to plug in my concentration over here. I know that's super ugly and whatever, but I'm sorry. So 22 divided by 400 is actually a pretty high concentration. That's going to be 0.055 molar. So now it's just like that first problem we did. So I have this fluorine still present, which is then going to, as equilibrium is trying to be established, and I see an increase in magnesium and an increase in 2x for the fluorines, right? We're going to see it overall decrease the solubility though. So x, and then we're going to have 0.055 plus 2x. Now remember, when we did this, I'm going to shift it over just a bit. When we did this before, we talked about how we would neglect the x, right? So I don't care about this plus 2 because my KSP value is 10 to the negative 9. That's so small, okay? So now coming back here, when I calculate the KSP, after the reaction has taken place, my KSP is going to be x. I guess if you want me to write the whole expression for you, I'll write it so that way we can see it. Mg plus 2, I skipped that earlier, but I'm going to write it just so that you can see it. F minus squared, right? So when I calculate the actual KSP, I know that, I still got to shift over. My KSP is 6.4 times 10 to the negative 9. It was given in the problem. And that's going to equal 0.05, no, leave that alone. What am I doing? All right, let's try this again. Let's erase that. No, I won't erase because I'm crazy. All right, we're just going to write over it. Okay, that's going to equal x for my magnesium plus 0.055, right, plus 2x, which we're going to end up neglecting squared. So we're going to end up getting rid of that. So 6.494 times 10 to the negative 9 is going to equal, and we're going to divide that by 0.055 squared is going to equal my x. So x is your molar solubility, but it's also equal to, because what it wants is concentration of magnesium, right, at equilibrium, because that's what that is. So that's going to end up being, when I solve for x, let's see, what do I get? 2.1 times 10 to the negative 6, right? Molar. And then I'm going to basically, to solve for concentration of the fluorine, I'm going to take 0.055 plus 2 times 2.1 times 10 to the negative 6. Now, hopefully, when you do this, you realize that's not going to appreciably change the 0.055. So my concentration of fluorine is essentially still, when you do the math, 0.055 molar. Because I had such a large concentration compared to the K value, or the equilibrium value. But I was able to find my concentration of magnesiums as well. So the solubility of it would also be 2.1 times 10 to the negative 6. So obviously the solubility decreases because of the fact that we have that fluorine present or leftover. If there had been less fluorine left over, then it would have had less of an effect. Hopefully that makes sense as well. So this kind of combined both problems that we just did. So one is, does a precipitate occur? The other one is, when there is common ion left over, how much of each ion is going to be present in the solution, which is going to be less, or how does that affect the solubility, which makes it less. So keep that in mind. So this was combining both of those problems together as one problem. That's why it took so long and had so much space taken up. Okay, the last problem. So I'm not going to work this one for you, but I'm going to kind of tell you what you're looking for in this problem, okay? Because it should be pretty easy to work. So it says a solution contains this concentration, right, of copper ions and this concentration of lead ions. So if you add iodine gradually to the solution, right, you're going to create lead iodide and you're going to create copper iodide. But one of them, right, is going to precipitate first. So we have to decide which one is going to precipitate first, okay? So really, this problem is kind of easy. When you're given the concentrations of both, and you have two, right, you basically just have two common ion problems in one. So what you're going to do first is you're going to set up two rice tables, right? And so when you set up the two rice tables, you're going to have one for each of the PBI2 and the CUI. So you'd have PBI2, and over here you're going to have CUI, okay? So you're going to have two separate rice tables. You're going to calculate the KSPs of each one. Of each. Not the KSPs. What are we doing? We're calculating the solubility of each. Sorry, I say that. I'm meant to say solubility. Calculate the solubility of each. Because really, all we're trying to do is calculate the solubility, or molar solubility, if you want to call it that, of each. All right? So we're really just trying to find what is the molar solubility of each one. The one that has the smaller overall solubility, right, would be the one that would precipitate first. The smaller solubility means it has less ions, right? That's really what it means. It has less ions dissolved. And so therefore, it's going to have a lower KSP in general, right? When we solve it. And so since it has the less dissolved ions and the lower KSP value, then we're going to see that one, then it precipitates less ions dissolved, then it precipitates first, meaning it will precipitates with the iodine first, because it's going to pick up those extra iodines faster than the one that has a lot. Okay, so it's really all you're looking for. You're going to do two separate rice tables, and then you're going to calculate that solubility of each. Remember, solubility is X of each. And then you're looking for the one that produces the smallest number of ions, or the smallest solubility. And that one would precipitate first. All right, pretty easy. I want you to do those two, so show me those two problems. This is a common ion problem, so you are starting with initial quantities of copper and lead. So that's the main thing, and 0 of your iodine. All right, so figure that one out. Let me know which one it is. And I will check your answers, so make sure you submit that with your notes.